Welcome to another Code Report solution video, the third one in 4 days. The Code Report YouTube channel is back firing on all cylinders because we are so excited about the Uiua programming language, a stack-based array language, previously a stack-oriented. That has been rectified. A link in the description to the documentation page that explains the difference. But first, things first. The ArrayCast episode that was mentioned, I believe, in the previous two episodes is now out, was just released a couple hours ago. It's available on Spotify, Apple Podcasts, Google Podcasts, all the podcast platforms. If you've been enjoying the last couple videos, be sure to check out this episode, if not the whole podcast in general. It's a fantastic conversation with the creator of the Uiua language, Kai Schmidt. You'll learn a lot more. And in this video, we are going to look at a comparison between BQN and Uiua again. Same thing we did in the last video because these are my two favorite programming languages. Which one is my favorite is still to be determined over the next couple days/weeks as I explore the Uiua language. Both are fantastic in their own rights. And we are going to be looking at a problem that actually I haven't solved on this YouTube channel, but I did solve it in a talk that I recently gave at CPP North 2023 back in June. It's a conference that takes place in Toronto, Canada, where I live. And I gave a talk called Composition Intuition, where I solved the problem called Sum of Squares. Let's skip over and look at a clip from that talk. Link will be down in the description if you haven't seen that talk already. And if you want, you can skip ahead if you already have seen the talk and skip to see the Uiua solution of that problem. But first things first, here's how we solve it. Live coding in BQN at CPP North 2023.
This is just the identity function right now, sum of squares. X is basically our omega in APL, so this is BQN. And the idea of the problem is, you can see we've got two test cases, and these are going to live update as I code. And the answer to the first one is 21. The answer to the second one is 63. We basically want to square the values of our integers, but only sum the ones where the index corresponding to that element is divisible into the length of the list. So for the second example, we have 6 elements. The indices 1, 2, 3, and 6 divide into 6. So we only want to sum the squares of those elements, and we want to ignore the other ones. For 1, 2, 3, and 4, 1, 2, and 4 go into 4. So we basically just want to omit the 3. It's going to be 1 squared plus 2 squared plus 4 squared. So how do we solve this in BQN? Moment of truth. First thing we want to do is take the length of our list. That's a single character. I'm not going to explain why it's the not equal to sign. It's just, that's just the way it is. Then we want to generate an iota sequence. We want to get the indices of our values. And this is one indexed, but BQN is a 0 index language, so we're going to use our iota, which is called range. And in order to get this to be 1 indexed, we just add 1. Pretty straightforward. Now what we want to do is we want to take this sequence and do the length of the sequence mod these values. So the way to do that is to basically put this in parentheses, add the modulus operation, and we are then going to put this all in a fork. And so what this does basically, we have a fork now, a binary operation modulus and 2 unary operations. This technically evaluates to an array, which is going to be our indices, and this is going to be our original length, which is 4 and 6. And so this is a fork, but one of them is actually the identity function here. So this is evaluating to 4 and 6, and we're just passing that in. So technically, we can make use of something called the sigma combinator, which is the same thing. So a lot of the times when you have a fork and one of your unary operations is fixed to the I combinator, that is also a combinator. So these don't exist in J or APL, but they do in BQN. So this is known as sigma, what's called backhook and I. But now we want to basically identify what are the ones that are divisible. And so they're the ones where the modulus corresponds to 0. So we just go 0 equals. Pretty fantastic. And I think we can actually get rid of these parentheses here for a moment. So now we have a mask, which corresponds to the values that we want to square and sum. So there's a couple different things we can do. We could filter, but filtering is not very idiomatic for BQN. So really what we want to do is we just want to multiply with the original sequence. And that zeroes out the values we don't want to square. And now we can square, which a really cute way of doing that is to basically call the W combinator, which is known as self, and apply that to multiplication. So we're now taking a binary function, multiply, and passing the same argument twice, which is square. And now once we have this, we just basically sum up our values, and we're done. Pretty nice, in my opinion. However, not point free, so let's do the point free thing. Point free is another spelling of tacit. It basically means this solution is mentioning our arguments here, x and then x again. Point free or tacit means you don't mention your arguments. Great question. That was from Matt. Yeah, I mean, so it's a bit confusing. There was a comment from Victor in the front that point free in Haskell usually necessitates actually quite a few points because the dot is the B combinator. But what a point is it refers to its argument. So it really is argument free, not point free. It's a bit confusing, but you know, what can you do? So if we want to make this point free, we go back to this, and now this is a unary function here. So the result of applying the sigma combinator to a binary function and this array is a unary function. And this is a binary function. And so implicitly, this is the B1 combinator. But if we go 0 equals, this no longer parses correctly. So there's a couple different ways to do this. My favorite is using this nothing, which basically says, don't try and read this as a 3 train, which would be a fork. Apply nothing here and know that everything to the right, that's just a 2 train. That is a point. It is a point. Good point. So now we have this. Now we need to multiply with our initial sequence, which that is this. So we can, once again, a couple different ways to do this. My preferred way, because it's the shortest, is to build a fork. So this is now basically a fork at the highest level where everything to the right is a unary function. This is your binary function, and then this is identity. And now, once again, so I could use the multiply W combinator trick, but instead, because I can keep on building up basically 3 trains, I'm going to do 2 power, but now this is the wrong order. So I need to flip the order that right now this is 2 to the power of our list of numbers. We want our list of numbers to the power of 2. Once again, this is no longer the W combinator, this is the C combinator. This is flip, because they're overloaded. Not going to talk about it because I've only got a few minutes left. This is one of the complaints about array languages, though, that I think is very valid, is that although this is incredibly beautiful in my opinion, there's a lot of implicit stuff going on here and overloading that you need to be able to read. I can read this stuff, so I know that in this context, power is a dyadic function or a binary function. So when this higher order function, this combinator is being applied, it's in the dyadic case, so it's the C combinator, it's the flip. But it does make it hard to read in a lot of cases. And now because we do this, we can do sum, and we're done. So this is the point-free version.
All right, so we just saw the BQN solution, both explicit and tacit. You're seeing it again here, the tacit version on your screen, and now we're going to build up the Uiua solution. It is pretty fantastic. Let's hop over to UiuaPad. And here we are in UiuaPad. And once again, I've chosen a problem that highlights why Uiua, with its stack and its array language superpowers, is so fantastic. First things first, we are going to do the same thing basically that we did in the BQN language. We are going to build up an iota sequence, or in this case, a range sequence. So we're going to get length, then we're going to call range, then we're going to add 1. Once again, our plus is prefix. So we've got 1, 2, 3. And here is the first part of the Uiua language that makes this so awesome. Because we need the 6 in order to do modulus with 6 at this point. In the previous solution, we used the sigma combinator in order to do that. I mean, first we use a fork with an identity, and then we switched that to the sigma combinator. But here, we already calculated this 6 at one point in our expression. And that was right after the length. So as soon as we've done that, and we need it again, we can just insert a duplicate at that part of the expression, and boom, on the stack. That's going to be the new phrase, folks. Boom, it's on the stack. So once we've got this, now we just make a call to modulus, if I can type correctly. And there we go, folks. So no parentheses, no sigma combinator. We are just making a call to duplicate at the right part of our expression, and then we've got the value that we need, or the array that we need, on our stack. It's fantastic, folks. Once again, we're doing a prefix equals compared to 0 in order to get a mask of the values that we want to square. Then, once again, we need our original array that we had. So we go to the front of the expression, we duplicate. Fantastic. It's on the stack. Now we just need to make a call to multiplies in order to zero out the values that we don't want to square. Now we've got a couple different options. We can call power 2 in order to square, or we can also do a duplicate with multiplication, because that is the same thing as squaring. I personally prefer the power 2 because it adds a little bit of spice to our solution. Either or is great though. It's just fantastic. And then all we have left to do is a plus reduction and we're done. Look at that. We can comment this out, realign the comments. Working fantastic, folks. It's unbelievable. And what's fantastic about this, I mean, you can do something similar in BQN. You need to call replicator or compress with the C combinator, the flip combinator. But here, when we're doing the multiplication, we could also replace this with keep to filter out the values. And we get the exact same answer. And I love the fact that you can just replace a single character with another algorithm. You can go from multiplication, which is zeroing out our values, which is going to be probably more performant in an accelerated version of this language. Like if you were trying to target a GPU with this kind of language, definitely doing multiplication instead of a filter where you're doing like a copy if algorithm in the background, it's going to be more efficient to zero out. But we're just playing around. We don't really care about performance right now. And the fact that we can switch between keep and multiplication with a single character, we can do the same thing here if we go back to our multiplication with our duplicate instead of our square. The possibilities are endless, folks. And look, there's no parentheses, no complexity of needing to learn the sigma combinator or the phi combinator or all these different combinators, which I personally love. But from a beginner perspective and a learning, coming to a language, it's very hard to master the paradigm of combinators, going from phi to S to phi 1 to D2 to S to back to S to sigma to D to delta. There's so many combinators and I love them. I think it's fantastic. I think it's elegant, but this is a simpler model that just makes use of duplicate. In this case, we don't even need flip the C combinator. It's just the W combinator, folks. It's fantastic. All right, I've gone on enough. Be sure to check out the ArrayCast episode. Look at that. Uiua pad. It's already plugged in ArrayCast. It's fantastic. And link in the show notes for both the ArrayCast episode, the composition intuition talk, and all the links to Uiua stuff, as well as the BQN pad stuff. That's it, folks. Hope you enjoyed. Hope you learned something. And we'll see you in another video, probably comparing BQN and Uiua again, because they're just fantastic, folks. And I do plan to release, at some point in the next week or so, a video covering the history of my top 5 programming languages. And I will be naming my favorite programming language of 2023 in that video. Have a good night, folks.